Hello everyone, welcome to the second episode of the video series for the AI data centers. In the last episode with Mikhail, we discussed the popularity and adoption of Rocky V2 and the advanced options it supports for proper congestion control. We also discussed how Rocky V2 components coordinate inside the DC fabric, particularly the PFC and the ECN inside the IP class fabric, and briefly touched upon the advanced options of Rocky V2 to get the proper congestion control settings with a few load balancing efficiencies emerging in the industry. Today, we will discuss cutting-edge technologies for load balancing and techniques for balancing flows from GPU clusters. And to kick off our discussion today, I'm joined by another special guest and good friends, Mahesh and Himanshu. Mahesh and Himanshu, welcome to our episode 2.
Thank you, Arun. I'm glad to be in the hot seat with you.
Thanks, Arun. It's great to be part of this discussion with you and Mahesh.
So, Mahesh, I'm going to kick off with my first question to you. Load balancing is not a new concept and has been a key feature in improving application performance by increasing the response time and reducing network latency for a long time. But why has it become a hot topic in AI infrastructure today?
Short answer, elephant flows with less entropy lead us to focus more on efficient load balancing in AI data center fabric, Arun. But to elaborate more, any AI infrastructure have two phases, training and inference. Specifically on the training, we'll connect all the GPU together. We'll call it as a GPU cluster to train the model. In the GPU cluster, a GPU will move the memory chunk to another GPU. And we'll call it as a gradient or memory chunk. End of the day, it is the result of the training. Within the server, for example, if you're using NVIDIA server, the memory chunk will communicate within the server between the GPUs via nickel, NVIDIA collective communication libraries. If you're using other vendor, they will call it as a nickel and all. But if you're moving that memory chunk from one server to another server, that's where you need a fabric. Moving the memory chunk, technically, we'll call it as a RDMA traffic. The RDMA traffic is so crucial because we need to synchronize those results across all the GPU in the cluster. Because it's so crucial and also so sensitive, because RDMA is a remote direct memory access. You are moving the memory from one place to other place using QPAD. Also, the RDMA traffic is large, less entropy. Because of the less entropy means it's a differentiation in the packet, right? If we have a good differentiation in the packet, easily we can segregate the traffic and spray or load balance across the parallel links in the particular switch. But if you don't have a much differentiation, less entropy, it's so difficult to load balance the traffic. If you don't have the proper load balancing in the fabric, of course, everybody knows there will be a congestion. There is a high probability of making a congestion in the fabric. When you have a high probability of making congestion in the fabric, of course, there will be a packet drop. When you have a packet drop, automatically your job completion time will go high. So to have a lossless fabric, to have a congestion fabric, load balancing become prominent in the AI data center cluster, specifically in the training cluster. So we must have a proper efficient load balancing in the AI data center fabric.
Now that we understand the importance of load balancing in the AI data centers, Himanshu, that brings us to my next question. What are the load balancing methods prevailing in the industry and also supported by Junos? And why are they good fit or may not be a good fit for AI data centers?
Yeah, Arun. So our Juniper QFX 5K switches currently supports two mechanisms of load balancing. The first one is static hash-based load balancing, and the second one is dynamic load balancing. So whenever a packet comes to a switch, what switch does is it looks into the packet header and it creates a hash out of it. Then it takes the hash and checks it into the flow table and tries to find if there is an entry existing in the table. So if there is an entry in the table, it is considered that the flow is already present and active. So it takes the outgoing interface map to that entry and forwards the packet out of that outgoing link. But if the entry is not there in the table, in that case, it is considered as a new flow. So the switch has to make that entry into the flow table, and for that it needs to find out a good outgoing interface. So with SLB, it basically looks into the flows mapped to each of the outgoing interface, and it finds which link has the least number of flows mapped to it, right? And then it assigns this flow to that outgoing interface. So this works out best in most of the cases where there are more number of flows, but the bandwidth within the flow is not huge. But in cases of elephant flows, this does not result in efficient load balancing. And that's how dynamic load balancing come into picture. So with what dynamic load balancing does is it has an algorithm wherein it takes the link utilization and the queue utilization and taking that into account, it goes through the algorithm and comes up with a quality band. It assigns quality band to each of the outgoing interfaces. So this quality band can range from 0 to 7, 7 being the best quality link and 0 being the worst quality link. So now looking at this quality band, it assigns the flow to that link and the traffic starts following. So with TLB, there are three modes of operation. The first one is assigned flow. So once it assigns the flow to a link, it continues to use that link forever until that link is until that flow is active. The second mode is flowlet mode. So with flowlet mode, what it does is once it assigns the flow to a link, it keeps on monitoring the flow as well. So it keeps on checking for a pause in the flow. If the pause in the flow is greater than the inactivity timer configured, then it basically considered that the flow is over, and the next packet it treats it as a new flow, and it again goes through the process of identifying the best link and assigning it to that link. So this is how it keeps on doing the rebalancing based on the pauses in the flow. The third mode is the per packet mode, wherein basically switch the packets within the flow are balanced across multiple links based on the link utilization. But as we know, per packet mode results in the reordering issue on the NIC side. So the destination NIC should have the capability to handle the reordering. So that is a challenge with the per packet mode. From AIML data center perspective, as Mahesh explained, that it has a lot of elephant flows coming into the picture. We think that DLB has a good potential there compared to the SLB.
Thanks, Himanshu. So that brings my next question to Mahesh. What's next with load balancing?
Yeah. So as Himanshu explained about SLB, we can call it as option 1 and static load balancing. And static load balancing doesn't have the intelligence to go and check the link utilization or link health. And so that's the reason we are going to option 2, which is DLB, dynamic load balancing. It has the algorithm, has the intelligence to understand the link health as well as the queue depth. And we'll call it as a quality band. And since you asked what is next, and the DLB, the problem is that the quality band, the quality information always will keep it in the same local switch. It will not propagate that information to other side of the node, a leaf or spine. So that's where the next one, the option 3 is coming to the picture. That's called global load balancing. Global load balancing is from a Broadcom ASIC. TH5 supports global load balancing. In our product also, we are doing it. But what it does, it will create the quality band and understand the link utilization and the queue depth, and it will propagate that information where DLB cannot do that. GLB can propagate that information from local switch to the remote switch, maybe leaf or spine. Which means the advantage here is that you will not only know the local link health, you will understand the whole path quality health. So accordingly, you can spray or load balance the traffic, specifically elephant flows on the RDMA traffic efficiently. We have option 4 as well. Option 4, we'll call it as a DLB version 2, or I will call it as a selective load balancing, selective DLB, I would say. What it does, as I mentioned in the earlier discussion, elephant flow is the key and it's crucial to look for it, right? So the selective DLB, it will go into the RDMA traffic. If that's a BTH header, it will look for that elephant flows. What are the elephant flows coming out of that RDMA traffic? And we'll call it as a RDMA write verbs, which is nothing but the elephant flows. So to identify the elephant flows, accordingly, it will spray the traffic. So to summarize that, there are option 1 for SLB, option 2 for DLB, option 3 for GLB, option 4 is for selective DLB. But one point I want to make it clear here, all those load balancing we are supporting, reordering is another key criteria we need to look into that. The reordering of the packet in the NIC right now, the NIC vendors are some other vendors are supporting reordering, which we need to handle carefully. So all the spraying can happen in the fabric. The NIC has to handle the reordering. That one point I want to make sure. Second, we are part of the UC Ultra Ethernet Consortium technical working groups. And already UEC started working on the flexible reordering. So it will create a new standard. Once the flexible reordering will emerge, there will be other options also come into the picture in the fabric level. As of today, we have 4 options, as I mentioned earlier.
Fantastic. So Himanshu, is the industry thinking about any further enhancements to DLB? And what is Juniper doing in particular?
With respect to DLB, Broadcom has come up with a cognitive routing set of features. Among them, there is a feature called reactive path rebalancing, which is an enhancement of DLB. As we spoke about flowlet mode, wherein it monitors for the inactivity timer in a flow to do the rebalancing. But with AIML workloads, it may not be that always there is a pause in the flow large enough to cause the rebalancing. So what this feature does is it keeps on monitoring the flow as well as the link quality of the link where the flow is going through. So if the link quality is not good, in that case, it tries to find a new link and assigns this particular flow to that link. So in a way, it will do the rebalancing even without any inactivity timer. So this is going to be very helpful with the long lived flows in particular. Other than that, Juniper is also working on providing some configuration option to be able to control the bucket size or the table size assigned for each of the ECMP next hop. So these are some of the aspects that Juniper is working on.
Fantastic. This is very insightful, actually, and more like a crash course on load balancing for me and for the viewers. But before we wrap, I need to ask, what other technologies do we see being enhanced in support of AI data centers? And Mahesh, you want to take that question? That'd be great.
Oh, yeah. Wherever we are talking about AI data center, Arun, the key word is that lossless fabric, right?
Correct.
So to build a lossless fabric, we can do it in different way, but to categorize it proactively, we can make the lossless fabric using a lot of load balancing, efficient load balancing mechanism, what we discussed now. The second is the reactive mode. So if there is a congestion, how we are going to handle, what are the mechanics to control the congestion? That's where the Rocky V2 come into the pictures. So the next will be congestion management topic, which will be really helpful to whoever watching this video. It will be helpful to understand how we can tweak that for the AI fabric. The other one is that thermal management, and its GPUs are greedy and more than switches, and that it will consume a lot of power. So how efficiently we can do the thermal management in the racks in the data inside the data center? That may be another topic. Yeah.
Fantastic. I think it's a great point to conclude here. But thank you both. Thank you, Mahesh and Himanshu, for a very insightful discussion. And to all our viewers who are listening in, stay tuned to learn more about the AI data center clusters in the next video and all the technologies that support it. So stay well until then.